it's fairly well balanced so that if I mess with it, it's trying to point in the same direction, basically. By balanced, that means I got rid of a gravitational torque. So now I'm going to screw that up. Now, is that uniform precession? It's uniform, right? See? No. How would you describe that? Bouncy, okay? So let's look at it again. I'm going to start it so you can watch right when I let go. Okay, so right now it's just spinning. So what's the initial motion? Down. Yeah, the axis has to dip, right? Why is that? Well, is it going around this way? Does it have any angular momentum up? It's spinning around this way. Not very fast, but it is going around, no? So doesn't it have angular momentum up? Okay, so that means there was a torque? Up? No? Yeah, what would cause that? What would cause an upward torque that makes it go this way? So you see, it's damping out, right? And it's coming as it slows down. It's coming more or less to a steady tilt down. So the angular, get back here. So the angular momentum of this spin used to be horizontal, but it's tipped down, right? As it goes around. So it has a vertical component that is down. And the rotation for going around has a vertical component that's up. See how those might be related? So that it stays horizontal. The total angular momentum stays horizontal. So while I'm into messing with its mind, oh, that was too much mess.
It's gone bad. You lost control.
Stop that. All right, let's see if I can get it to... No. It's getting closer. So what I'd like is it to just go around uniformly. And if I set it up with the right initial condition, when I get to supply whatever torque it wants, then presumably we can get the rotation to match just what it needs up there so that it goes around at a uniform precession rate. How does the precession rate depend on the tip angle? Assume that it's spinning at the same rate and compare the precession rate when it's straight out to when it's tipped down or up. Okay, so let's see how we're doing here on precession when we're tipped. So this is the horizontal. Let's tip at some angle, I don't know, alpha with respect to the horizontal. So if we've tipped the gyroscope up that way, what happens to the gravitational torque? Okay, tau gravity would be something like mg d times which trig function of alpha? Cosine because the center of, so let me make the wheel be out there symmetrically. So gravity is being applied that way, and now the perpendicular distance has been reduced from d to d cosine. Well, take a look. Let alpha go to 0. Imagine alpha goes to 0, then this comes down, and the distance is all d. So at 0, that's a terrible cosine. At 0, we get everything. Okay? So that means we reduced the gravitational torque. And then what about the angular momentum? Well, now the angular momentum has a component that's up, and it has a component that's radially out. Right? Do we agree? So, what happens to this component? It develops a change into the board. So dl horizontal dt would be equal to tau grav. But the horizontal component of the spin is L spin times cosine of alpha. So d of L spin cosine alpha dt is equal to mg d cosine alpha. And so the cosine alphas just drop, and the rate of precession is independent of the tip angle.
So that my students don't yell at me in recitation, can you erase the arrow from above the tau?
Can I erase? Oh boy, thank you. That was evil and rotten.